Okay, so this is the hybrid part of section 9.5 on solving trig equations. So picking up with example 7, we want to solve sine 2x equals sine x. Now something to note about this one. This is a double angle right here. This one's not. So we need to make sure these arguments are the same before we kind of move any farther along in here. So I'm going to use the double angle formula for the sine function. So we know the double angle formula for sine 2x here is 2 sine cosine. So again, this is the double angle formula, back from our formula sheet, right here, cleverly labeled double angle formulas. Now, once I get that double angle formula in there, you can see now all my arguments are x. So I'm going to subtract sine x from both sides to get a 0 over here. I can factor out a sine x that's common to both of those terms. And when I do, now that I have this equal to 0, I can use what's called a zero factor property, and I can set each factor equal to 0 and solve those separately. So sine x equaling 0. And then 2 cosine x minus 1 equals 0. So let's start with the sine x equals 0. We have 3 options for that one. If you look at the graph of sine x, you can see that it does touch 0 at 0, pi, and 2 pi. Now that's the same as 0 and 180 degrees. Why did I cross off 2 pi though? Because the interval that we're interested in only goes from 0 to 2 pi, but remember that parenthesis right there means we're not including 2 pi. That's because of the repetition, right? Usually things at 0 and 2 pi have the same value. So we choose to include 0 but not 2 pi. So that's why. The 2 cosine x minus 1, if we add 1 to both sides and then divide by 2 to isolate that cosine x, we get cosine x equals 1/2. So what angles have a cosine of 1/2? Well, 60-degree angles, and because it's positive 1/2, we know it's got to be in quadrants 1 and 4. That's the 2 quadrants where the cosine function is positive. So what are the 2 angles that have a 60-degree reference angle in quadrants 1 and 4? Well, it's 60 and 300 degrees. So there are my 4 solutions. So I get 2 solutions from the sine x equals 0, and then I get 2 solutions from the cosine x equals 1/2 business. Again, going backwards here because we're looking for the angle whose cosine is 1/2. So knowing that that's 60-degree reference angle, it's a positive 1/2, so it has to be in quadrants 1 and 4 because it's a cosine function. So 60 degrees in quadrant 1 is just 60 degrees. 60-degree reference angle in quadrant 4 is the same as 300 degrees. So this is a lot of that first chapter that we covered. Example 8, we're going to solve 2 sine squared minus 3 sine theta plus 1 equals 0. This one kind of has a quadratic feel to it. So that's how we're going to look at it. So all I did was replace the sine function with x so that this can look more like 2x squared minus 3x plus 1, which we know will factor into 2x minus 1 and x minus 1. So that means because I replaced sine theta with x, putting the sine thetas back in there, this will factor into 2 sine theta minus 1 and sine theta minus 1. We can split those up and set each one equal to 0 and solve those separately. So 2 sine theta minus 1 equals 0 is over here. I'm going to add 1 to both sides and then divide by 2, so we get sine theta equals 1/2. What angle is associated with the sine function in 1/2? Well, that's 30 degrees. It's positive 1/2, so it's 30 degrees in quadrants 1 and 2. That's where the sine function is positive. So 30 degrees in quadrant 1 is just 30. 30-degree reference angle in quadrant 2 is 150 degrees. Over here, sine theta minus 1 equals 0. If I add 1 to both sides, I get sine theta equals 1. This one you can use from the graph, or you can do the inverse sine of 1 and get 90 degrees. But this one you would just look at the graph of the sine function and say, okay, right there is where it's 1, and that value right there is that pi over 2, or that 90 degrees. So the tricky part of this one was recognizing it as a quadratic that was going to factor. Once you get it factored, then that whole splitting and setting it equal to 0 should be a little more familiar now. All right, we got another one where we have a double angle going on here. Now, this one's a little trickier because the cosine double angle formula, there's 3 choices for that. Right, we have cosine squared minus sine squared, we have 1 minus 2 sine squared, and we have 2 cosine squared minus 1. Because this is a cosine, I'm going to pick the double angle formula that has a cosine in it. I don't want to bring in another trig function if I don't have to. So I chose the 2 cosine squared minus 1. That way everything's in terms of cosine. Combining like terms, that's going to zero off. It's going to give me 2 cosine squared x plus cosine x equals 0, which is nice because that means this factor is easier than the last one. The last one being a trinomial, it was a little tougher to factor. This one we can factor out a common factor of cosine x and get 2 cosine x plus 1, and then we can do the split. Cosine x equals 0 means that x is 90 or 270. We can get that again from the cosine graph, looking at where it intercepts the x-axis. 2 cosine x plus 1 equals 0. We'll subtract 1 and then divide by 2. Now we're looking for the angle whose cosine is negative 1/2. It's negative, so we're going to pick the 2 quadrants where the cosine function is negative. The angle associated with 1/2 and the cosine function is 60 degrees. So we want a 60-degree reference angle in quadrants 2 and 3. So that's going to give me 120 and 240 degrees. So it's really important that you guys understand the quadrants, the reference angles, all of that stuff, because all of that stuff really comes into play here. Once you get down here, all that stuff really is super important to be able to figure out the angles here. And then one more. And this one's super nice because it's already factored for us. So that is awesome. You see, it's already factored and set equal to 0. So we can just say, hey, sine x minus 3 equals 0. Cosine x plus 2 equals 0. We're going to solve these simultaneously here. I'm going to add 3 to both sides, get that sine by itself. What angle is associated with 3? That's a weird one here. But if you use your calculator and you take the inverse sine of 3, I'll draw here and grab the calculator out. So if you were to take the inverse sine of 3, you're going to get an error. Now, not just an error, it's a domain error. You want to pay close attention to your errors. If it's a syntax error, that means the calculator doesn't understand what you're trying to tell it. It doesn't understand what you want it to do. A domain error means, yeah, that's not happening. That's because the sine function never goes above 1 and never goes below -1. So there's no solution. Over here, if I subtract 2 from both sides, I get cosine x equals -2. Same thing, no solution. The cosine function never goes above 1, never goes below -1. If you tried to take the inverse cosine of -2, you're going to get a domain error as well. So those are going to have no solution. I just wanted to do one that was going to have no solution so that you could see what that was going to look like on the calculator and, you know, how that how that could play out. So, all right, that finishes up the hybrid portion of section 9.5.